All right. And now we are finalizing our last question before we get to the extras for this chapter. So that was a fun run through, but of course, well, we can't have fun without finishing on a strong note. So let's see what we got going on. So what we have is for the configuration in problem 10.15, we saw that was a circular one. Find the electric and magnetic field at the center. From your formula for B, determine the magnetic field at the center of a circular loop carrying a steady current I, and compare your answer to the results of exercise 5.7. What we need to know, okay, we have the electric and magnetic fields with regards to the constant velocity point charges. Here, what was known was that we were moving in a circular motion, radius r. The angle was omega t, so Q was somewhere on the circle in the xy plane. And now let's just start tackling along and define all these parameters. From problem 10.15, we parameterize this path that the charge is taking the circle in the xy plane with radius r, and now we can rewrite it. So again, here I'm using the angles to denote the vector brackets, not the average bracket, not the time average bracket, or expectation value, whatever you want to call it. That's not the case. Vectors only. I'm tired of writing the unit vectors. You can call me lazy if you want. I'm cool with that. But anyways, we take the derivative, and then we take the double derivative so we can find the velocity and acceleration as such. We see very quickly that the acceleration is just negative omega t w. Pretty good there. Pretty easy to deal with. Well, again, since we want to find this at the center, script r is equal to 0, 0, 0 minus the wt at r, evaluated at the retarded time. So we get negative wtr, and then clearly here, script r magnitude is equal to the squares, so that's just equal to capital R. And then the unit vector moves on pretty quickly, I would say. Just divide the two, and then the r's cancel. Okay, so with that being said, we also know the retarded time is t minus script r over c. Script r is just r, so we're good to go. All of these things seem very natural for circular motion. So let's plug in and hope we don't lose ourselves in the coming vector calculus. So now that we have all the parameters, let's just start calculating. Recall that u is equal to c script r hat minus v evaluated at the retarded time. So let's find out what this actually is. You see we have no component in the z direction, but we have the x and y that need to be accounted for with the c's and v accordingly, so be careful. The reason why is because now we have r times, or not times, cross u cross a. Again, this is a triple cross product or a double cross product, or so a triple product. We could use the back-cab rule. So it turns our cross products into dot products. That being said, let's use them accordingly. R dot A, that's equal to a couple cancellations of negatives. We like that. I'll let you see that through. That gives you a omega squared r squared. Again, the dot product of the function w at tr just gives you cosine squared, sine squared, so they cancel to 1. We like that. Good enough. Script r dot u, you see we've got to be very careful with all the components. X is going to x's, y is going to y's. You see we get a lot of cancellation, so be the utmost of careful when distributing everything. Use the cancel line so we could see that the r squared omegas cancel. That being said, we still need to factor out an RC, so that gives us a square cosine and a square sine. We love to see it. Thank you, Pythagorean identity. And thus what we see is that the triple product is now the dot products come in, and we just see that we have an omega r squared times u minus an RC times a. And now we can plug that in. All right, so what we see here now for the electric field is we got the Q over 4 pi epsilon naught that never leaves our site. And then that dot product of R and U is put to use, so that's RC, right? Yep, that's RC, so that's cubed. Now that V squared, we have to turn into the, instead of linear, we have to turn that into angular, so we have to use omega R for that. And then once we do that, we'll see exactly why in the next step. For the triple products, substitute in. And then you see here that when we substitute in for the V squared, the omega R U, and distribute that with the U vector, we get C squared U minus omega R squared U plus omega R squared U, so the omega R squareds cancel. Love to see it. And then we were left with a C squared, now that we have those U's canceling, both of the terms remaining in the bracket have a factor of C, and that can cancel out. Similarly, that R cubed in the denominator can cancel with the 1 in the numerator. The highest or the lowest common factor is only 1C, so we can only cancel down to 1. Cool enough. And we said we have Q over 4 pi epsilon naught, 1 over R squared C squared, C times U minus R times A. Wow, that reduced down quite nicely. All right, cool enough. So then we'll just put that in the numerator and re-square the RC. Now we can actually plug in what U and A are and try to simplify this down to the utmost of everything. So I'm just going to let you see what the U and A substitution is. I think we know very well how to do adding and subtracting vector components by now. So I'm just going to go down to the vector formulation at the end. So we have Q over 4 pi epsilon naught RC squared, and in the x direction we have omega squared R squared minus C times cosine evaluated at the retarded time plus omega RC sine evaluated at the omega time at the retarded time, And then for the y, we have similarly just switch cosine and sine, again with the minus sign, just be careful. And then z is 0 again, nothing unwarranted, I would say. Now, of course, here we go with the cross product of script R and E. Blah, gross, but is necessary. So what we need is 1 over C, script R hat X, and then EY minus script R hat Y, EZ, or EX in the Z direction. Okay, so now that we know what components need to go where, we can handle this with ease. Okay, again, a lot of other multiplications to deal with. And then if you look, after we multiply everything through, we get some gnarly cancellations. So with that 1 over C term cancels out with the C's that are remaining in the curly brackets, as well as a factor of that R. Okay, that is pretty phenomenal. We like to see that. We like to see that a lot. And then ironically, after we factor this out and factor an omega out, what we're left with in the curly brackets is a cosine and sine squared again. So after we simplify down as much as possible, we see that we have Q over 4 pi epsilon naught omega divided by RC squared in the z hat direction. I mean, that's pretty cool to me. The graphic looks pretty cool in the book too, can't lie. But that tells you that we have angular dependency for this thing, and it's going to get messy pretty quick. At least graphically, that is. But what we can notice now is that B is constant in time. So to obtain the field at the center of a ring of charge, say let Q equal lambda 2 pi r, because that would be the charge on the ring. For the ring to carry current I, we would need I equal lambda V, but V we know has to go in angular, so that's omega r. So lambda would have to equal I over omega r. And if that's the case, then Q would look like I over omega r for lambda cancels with the r from the 2 pi r, and Q would go to 2 pi I over omega. Okay, so all we're doing is trying to form match this thing through. Okay, and exactly what we see here is that the 2 pi will cancel when we substitute it into the B field. With that 4 pi in the denominator, the omegas cancel. I color coordinated as much as I could. C squared, we can substitute in the epsilon naught mu naught, and the epsilon naught cancels. and we're left with mu naught I over 2R Z hat. Okay? And this is the exact same equation as 5.41, or the equation of the ring, for the case of Z equals 0. Dude, I don't understand how this is so consistent, but it is so pretty to see the things come together. If this doesn't get you excited, then, we gotta do some more reflection and more problems, because this is awesome.